Yes, good morning, everybody. I hope you hear me properly. Welcome to this second day of our training school and workshop on dust aerosol monitoring. As for last day, my name is still Federico Fierli, and I introduce you to this workshop on behalf of our partners and organizers. So EUMETSAT, that is the European Meteorological Organization for the Satellites, and we do this activity. We are happy to organize and to provide you this workshop, this training activity, together with the AMET, Agencia Estatal de Meteorología, Barcelona Supercomputing Center, together with the SDS Bus service of the World Meteorological Organization. And this is done also with support of the ACTRIS infrastructure, European infrastructure for observation, and within the Copernicus European program. So I won't take additional time. You have probably already seen this, so the objectives and the aims of the workshop, and I would like to remind you a little bit the outline. So what we are doing this week and what we'll do the next one. So this week we are here. We are working on the wash-up of the webinars, the presentations that you have on the course web page that you may see or you may have already seen, watched in the previous days. And we have a live discovery session with assignments that will be animated by our colleagues Julia Wageman and Zeto. So today the session will focus more on the different type of data sets, so data in situ data, and we'll also dedicate it to a review assignment that was given. Then next week, there is an even more interactive workshop, so an activity where you divide in smaller groups of about 10 to 15 people, and you will have one instructor, so Sabrina and Julia, that will guide you to specific real cases. And here is the problem. So today, we start with, as yesterday, with the question and answer on the webinars. We have all the lecturers, the experts that are there with us, so we introduce them. Then there is you will start the part of the practical, so the data practical, so with the review of the assignment that was given by Julia and Sabrina 2 days ago, and then the second part of data discovery. So you will again have to confront the data sets. Here again is the access to the material and the virtual places of the workshop. You will have also them regular chat. So basically you can use the Slido app. The Slido app the Slido system is very important for us for the question and answers. So you can put any question that you have here. In Slido, there will be also questionnaires, polls that we really kindly ask you to fill. So there will be now a poll about your evaluation of this first part of the course, this first week, these first 2 days. It's very important for us having it because it's really a way for us to improve and to do better next time, to understand what was good and what wasn't. As mentioned before, you have the course page here available on the course, and all the material, all the Jupyter notebook that Julia and Sabrina showcase you are available both in the Git repository, but more importantly, you can log in to the site, the other platform, then you can enter and you will be in the same environment that Julia and Sabrina will work on. So you can follow interactively the demonstration. I stop here. So you will have all these links again also thrown in the chat in order that you can directly access to this. And I would like to introduce our colleagues, our experts. experts. So I think we have Sara Bazard from BSE, from Basel Supercomputing Center. We have Lucia Mona, CNR, and Lucia is expert, our super expert in ground-based remote sensing data. And I think we also have Anupaya Sundström from Finnish Meteorological Institute that gave the lecture, the material for the satellite observation. And I don't know if Ernest is also with us. So Ernest Werner from EUMETSAT, and is also representing the WMO, and together with Sarah, they manage the forecasting system from that is implemented, the WMO forecasting system that is implemented by the Barcelona Supercomputing Center and by EUMETSAT, the Agencia Meteorológica. Okay. I shot myself, and I really would like to leave the floor open for any type of question that you may have in Slido, or even in the chat. Hello. Okay. Looks like that there are no much fresh questions, but if I remember well, one of the big points that was there were 2 points that were raised at the last time. So one is the usage and in fact the role of dust for climate, and another one is how, for instance, discriminate how to discriminate, for instance, or other natural events or pollution events from dust. So I do not know if we want to have the view on this from both from the model and from the observational side.
From the observational side is Anupaya and Lucia, basically.
Yeah, sure. It's not only you.
I mean, from the modeling point of view, at present we have nice climate models that are getting more and more complexity, and we are adding more and more processes for doing really like these future scenarios for the associated to climate change and the anthropogenic activities. And basically the big uncertainties are related with change in the land conditions, meaning the desertification. Then it is quite complex, this part, but also is the research community in climate is trying to assess better to understand the really processes that in which dust is involved. It's not just when dust is emitted, it's what is happening when the dust is in the air, or when dust is removed from the air and deposited on the oceans, cryosphere, land, any ecosystem. Then there is a lot of groups that are doing research trying to implement more processes and to understand the links and to improve this complex situation. And probably in future, there will be more advances, and we will go for constraining more and more the uncertainties that nowadays we have associated to aerosols. Yeah. This, from the perspective of the modeling, I think that this is the summary. And also the mineralogy, that this is a hot topic now, and the high latitude dust, how is impacted in our future climate, I will say.
Yeah, and for instance, how reliable is is the discrimination that you can have with the forecast models, also the analysis in the type of dust that you have over a certain location. So let's imagine, I am in the island of Crete or in Cyprus.
Okay, when we
And,
talk about climate, it's not the same that forecasting.
No, absolutely. No. This is another part. This is the second.
The problems that we face are completely different. Then for forecasting, when we think in forecasting, the long range transport is quite nicely reproduced, but for global and regional models, meaning that a huge plume of dust that is coming from Sahara and transported is well tracked by the models. The problem of the models basically is these spectacular sun and dust storms that we call it hawoops that are associated to convective systems. And if there are here some Met officers, I would like to ask them if it's easy for them to really predict a huge storm that is really localized, that is convective. And then in these situations is when if you are over a source of dust, you will have this wall of dust that is covering a huge area and is reducing the visibility to less than 1 meter. Then the models are more limited in these situations, but when you have a well-organized sun and dust storm, I mean, you can trust nicely on them.
And what is the point of view of the observations for satellite ground-based phones to take a read for?
Yeah, so for the satellite observations, so of course I think they serve as an important input for models, but also as they are, so you have already hopefully managed to do some hands-on exercises using the different satellite data. So we have a couple of products that quite well can observe the dust. There are still some limitations, of course, as it's always with the satellite data. And so I think the satellite data is like most usable in this kind of near real-time monitoring and seeing where the dust plume is. So the main parameters that we have introduced in the course are the absorbing aerosol index, which is sensitive to absorbing aerosols, and dust is absorbing type aerosol. It should be also remembered, I hope that you have watched the lecture, but the absorbing aerosol index is also sensitive to smoke. So it's not only dust that it is showing, but you need to always like analyze where the dust, where the plume seems to be originating from. So that might give you some hint whether it's dust or smoke, but that should be remembered. And then the other parameter that we have been introducing is the aerosol optical depth, which is sensitive to all types of aerosols. So this is also a good implication, and maybe a better one as the absorbing aerosol index if you think about air quality topics. But also here you should remember that the satellite observations, the aerosol optical depth includes all types of aerosols. So you need some kind of additional information on really determining whether the elevated aerosol optical depth is really dust or not.
Mm-hmm.
Yeah, so that is, but the satellites are a very good way to like have observations and large scale observations. So then if you then, on the other hand, if you want to go like very detailed aerosol mass PM10, so for those satellites are too coarse and contain too much like uncertainties, but satellite can give you kind of a broad view of the dust plume. But always keep in mind the limitations of the satellite observations that I want to always emphasize, and maybe the best result on assessing, for example, air quality. So use model data, satellite observations, and in situ together. So then you will converge to the best estimate.
Yeah, I can complement this with the in situ part. Because as Maya said, satellite observation are really great for providing you a snapshot of the situation on big areas and the distribution of the aerosol in general, and in some cases of the dust in particular. But if you want to have more detailed information, as Amaya said, in situ data are really relevant, and this can be used also for assessing and understanding better how it is possible to discriminate between different kinds of aerosols. And this would mean put together information from remote sensing technique like LiDAR, but also with in situ samples where you can collect PM1, PM2.5, PM10 information, and in principle also chemical investigation of on the samples. And all this kind of info collected in less places, of course, of the world, because it's a limited. There is the limitation, the possibility to have measurement in every place. But these are very relevant for validating and evaluating satellite data, as well as the modeling ones. So this is very nice to have the combination of the three components for trying to gain information on the aerosols, and in particular on the dust. So one topic which I see is really a hot topic is the discrimination between the different kind of particles in the air, because this is a very difficult issue in terms of nomenclature, of semantic vocabulary, but also in the content, because even desert dust is something very huge, as Sarah said. The mineralogy play a big role in the optical properties that you can observe, and in all of the things that can be measured by satellite and by in situ. So this is a very good topic to be addressed. Yeah.
Yes, I mean, I have put it as a satellite image because I think it's quite explanatory. Now the fact that, I mean, basically from satellite you have a global view, but it's difficult to discriminate among different types of aerosol or particles. Because I mean, what we expect, for instance, is that what comes out from a polluted region, the mineralogy of the dust, the forest fire that is made of burned biomass, they are different, and they have different impacts, for instance, on climate, as we have seen. But I mean, in some way, the satellite observe from top and has a limitation to discriminate this. The models may have uncertainty, in the position, in catching one event, as Sarah said, for instance, if the event is generated in a very localized way, and we also know that I mean, you can have a very intense sources that may be missed. Then I mean, because in principle model can discriminate because it has a different treatment, or you can put any type of source there, but you have this type of uncertainty.
In fact, the collaboration between the satellite and the in situ and remote sensing communities and modeling is clear, because there are a lot of synergies where we can exchange this contribution on the information that the model can do, filling the gaps of the observations, and then trying to understand better what is the kind of information that we can gather from each of these data sets. Okay. Yeah, it's fundamental. And one thing that I remember from yesterday, I don't know, Rosa, if you can recover some of the questions, was that there are some, we are talking a lot about the specific parameters, and I remember I tried to answer this question because someone was asking what is the meaning of the position and things like that.
Yeah.
And I remember, because I tried to put a link to this question. I don't know if this person is here today, but basically the dust cycle and the aerosol cycle and any reactive gas cycle starts with emission, that is a flux, and then these emissions put the reactive gas, or like ozone, NO2, or aerosols, or specifically dust, in the air. Then when dust is in the air, there are different processes that are the same than, let's say, for example, the humidity. How is the tracer that is dispersed, diffuse, and you can do it. And then there is a part that is the removal of these particles from the air. that we call deposition. And it's basically there are two main mechanisms for removing aerosols and other components of the atmosphere from the air. That is the dry deposition, that is basically the gravitational setting and the dry deposition on the ground. And then there is the wet deposition, that is basically when you have a precipitation event, is when dust is removed because the action of this precipitation. And just for your info. And then when we talk about AOD, is the column, load, and is an optical property. And we can also mention mass concentration, that is the amount of mass of this aerosol in a volume, that in our case, the volume is the atmosphere, or a part of the atmosphere if you think in surface, for example. And I think that I forget any key parameter. No. And extinction is also an optical property that is giving you an idea about the amount of aerosol in a certain volume. That can be the whole atmosphere or can be a part. This is the basics.
Okay.
I don't know if this person is still today here, but it's a quite basic parameters in the air quality and atmospheric composition community.
Mm-hmm. So I do not know if this can help, for instance. So how, let's say, how the different parts compose, generated the budget and determine the budget of anything. So if X, as Sarah said, is a mass of, for instance, of dust, of course, we have the emissions that we have talked a lot, but you have the process of deposition. And at the end, the mass balance, so how much the amount change in a certain point is the difference between sources of what is emitted and the sinks. So you have the transport here. You have the part of the chemistry that is not negligible, for the aerosol, or at least not all the aerosol, but at least for the dust, let's consider it inert from the point of view of chemistry. So there is no chemical production. But you have, of course, emissions, and you have the deposition that Sarah just said. So deposition can be extremely effective. Just think about precipitation that has, for the dust, has a very effective removal. So you drastically change the amount. And maybe if I can add one point, is the different type of observation. So Sarah said that you can measure the mass, for instance, also with the EC2 observation, so with the filters. So you measure the mass. So you accumulate the mass per volume on the filters, and then you weight them. So it's really direct observation. And for instance, mass is fundamental also for the question of health. So how much particles can you inhale in certain situations? While, for instance, the optical part, you want more to know which is the size distribution and which is the effect of the atmospheric particles, the atmospheric aerosol, for instance, on the radiation. So how much radiation is scattered, how much radiation is absorbed. And this is important for the loss of visibility. And then, for instance, it is also important for the climate part. So the climate part means that you need to quantify and to estimate the role of the aerosol on the radiative budget. So the absorption, the extinctions, and then, for instance, information like the optical depth is crucial. Okay. I do not know if there are any other direct question today, or if you want to give a second round to the questions that we had 2 days ago, and then move to the demonstration part. Okay, I can probably share. Okay. Okay, I think we have somewhat addressed all of them. So it's about the models. So we had the demonstration of the model from, I mean, of the new
It was me. It was me.
Yeah, yeah. From BSC.
It's basically the link to the WMO DAS regional center that I
Okay, and
don't.
you have it here. Exactly. Okay, I would like to know why it's so important to study different data sources, natural and anthropogenic. I think we have provided the several facets of this answer. I don't know, maybe there is this question of natural versus anthropogenic dust. Is there any?
Basically,
Yeah.
the definition of anthropogenic sources is coming from agriculture.
Mm-hmm. Okay.
Also, desiccated bodies like rivers, delta rivers and lakes that are desiccated because the human intervention.
Mm-hmm.
Also, the farming and the mining are considered anthropogenic sources. And I don't know if I have the full list. Also, some people considers the resuspension of dust due to the action of the traffic in big cities in the Middle East, for example, in Africa, a source of anthropogenic dust, but the definition is quite still depending on the community. Basically,
let's say it's also indirect anthropogenic.
Yeah, exactly. Then why is important? Because the natural sources are well identified, and we understand that are basically hydrological sources that are coming from ancient times, like the Sahara. Sahara, at the beginning of the life of the earth, it was an ocean, and now it's a desert, but it's a well identified source, for example. And the difference with anthropogenic is that the variability and the reason why these sources are there. Then it's for us to understand how, where are the sources and what are the mechanisms that can forward these sources. It's key for climate change studies. And also because it's important the factor of the desertification also, how the human intervention can extend the deserts or can desiccate areas that are more sensible and vulnerable. Then why is it important? Because if there are more sources, probably there will be more sun and thunderstorms, and this has clear implications in society and climate. Yeah.
Okay. I think we have almost touched all the other questions, so we are basically on time. And if you can probably hand over to Julia and Sabrina for the practical part, unless you want to provide further input or further relevance to the audience, or if the audience wants to raise some points. But in any case, still make use of Slido. So put questions there. We'll review them regularly. Also, we will answer as we did the questions that you put here offline. Yeah, thanks again to Sarah, to Maya, to Werner, Ernest, and to Lucia for supporting and intervening this morning. And yeah, I just pass the ball to Julia and Sabrina for the data discovery session. Okay, thank you very much, and enjoy.
Thanks a lot.
There's one question in the chat that just arrived. Do you want to take it or just?
Yeah, we can take it. I don't know if Sarah has disappeared. It's a lot for her, but is how to improve the dust forecast using a model. Or maybe how to improve models for dust forecast. But, let's rephrase it like this, probably.
For the next time, you have to invite two modelers to this.
Yeah, sure. But I mean, If you want, I can help you. I can give you the satellite point of view.
Please go. I mean, it is important that this perspective. I mean, it's key in operational. It's really key. Then go ahead, Federico.
Ah, okay. No, I mean, basically, the point is, as correct me. I mean, the model can have uncertainty in the predictability, and means that you can predict, do not predict the event, predict it at the wrong place or at the wrong time. And in fact, there is a level of predictability that depends on the circulation that is used for the transport of dust. And I mean, there is an intrinsic limit that comes from the analysis or the forecast that we use. For what concerns the dust process, I think Sarah probably would like to elaborate on that. But one of the big points, as you have seen, are the emissions. So from where dust, but also if we think about air quality, from where the emission comes and how intense is the emission. And one of the, I mean, the points for one of the aspects to improve, for instance, is to use observation to constrain the analysis. So start from the best analysis. So the best initial condition as possible, and to do so is use the assimilation. And in that sense, satellite data are extremely useful because, I mean, despite the fact that satellite data doesn't tell the mass that is what comes in the model, what is treated explicitly in the model, they tell where and how extended and which is the shape and the evolution of the satellite burden or of the satellite effect on the aerosol optical depth. And this is, I mean, extremely important to start from the best initial condition, because I mean we have to remember that the best is the initial condition, the best is the forecast. I don't know if you want to add other.
I will invite Ernest to add something because he is
sure.
a meteorologist. Then probably he can do.
Yeah, I wanted to add something because the other day somebody asked about the large spread that we have in the forecast from the different models. And this, of course, the models are different, but to have a large spread is not something bad, because could be something just a measure of the uncertainty that we have for a given meteorological situation. So the chaotic nature of the atmosphere is somehow reflected in the situation. So a larger spread is also a measure of this uncertainty. And using probabilistic products or multimodal products helps to assess this uncertainty and to give a probability to the possible different outputs. At the end, we're going to have just one output, but before that, it's very useful to have this measure of the probabilities of the different outputs. So, well, okay.
And also, I will complement your words, just saying that the question is how to improve dust forecast using model. Then models are giving you a perspective at 3 days ahead that probably only satellite data or in situ data cannot give you. Then the idea to complement all these sources of information is to give you a short, but also like 3-5 days ahead, you can know if there is potentially an event, and then you can alert the people in advance, or you can start to plan something in advance if you know that something is coming. And just the observations are not telling you this, for example. The observations are very useful for tracking something in the next hours, but not in the next days.
Yeah, then, what we call nowcasting.
Exactly.
Or then, I mean, it is a
window of 6 hours.
Period that is between very close forecast and nowcasting and the situation.
Of course, for me, everything is useful, and you have to know how to use it properly, basically. And this is the kind of intentions that we have when we organize these trainings,
That's
Then-
what we would like to do. So
Yeah.
we don't take additional time unless unless there are other questions. No, there are questions. Okay, you see, it's improving dust source mask, then better horizontal resolution along with improved emission scheme, then assimilation of is an answer from Boyan.
Yeah.
Yeah.
His model Aerosol. For the next time, Bojan, maybe you
Should,
can come to the panelist.
Yeah, absolutely. I mean, if you wanted to say something, Bojan, it's okay. Yeah, we are happy to hear you.
No,
More
thanks for
victims.
now, but thanks.
Okay. Yeah, and if you want, Boyan, I can also add the question of the deposition that was mentioned before. So the intensity, location, and of the deposition of the wet deposition. I mean, dry is maybe gravitational is quite okay, but I mean wet deposition. So the interaction with rain and the occurrence of rain is not the models that are used for that. They rely on I think on the rain forecast that comes from SNWS that are good in general, good forecast, but rain is very difficult to predict. So you can have clouds that are precipitating, and then you don't have precipitation in the real life, and then you have the process of deposition that is on or off. So, okay. If you have, there are no other questions, point you would like to raise or to discuss. Again, we hand over to Julia and Sabrina, and thanks again to all of you and to the audience and Ernest, Sara, Lucia, Anumaya, and Bojan. Okay. Please, Julia, that's your floor. Now you have to put in practice what we say. So.
Today,
you,
Sabrina
Federico.
will start the session.
Great, good. So please, Sabrina.
Thanks, everyone. Thank you, Federico, and thank you to our lecturers for also providing their insights. We will take a little bit of time now to also take any questions about the notebooks from yesterday. Are there any questions about the satellite data that we covered or the notebooks themselves? Feel free to post a question in Slido or in the chat box here. We can also take your questions. I will share my screen to keep an eye on the Slido page. I don't see any questions at the moment. So if there are no questions at the moment, let's move on to the material that we'd like to cover for today, which will be looking at ground-based observations as well as model forecasting. So let us switch over to the Jupyter Trading Hub. If any of you still have any troubles getting on this platform, please let us know over chat and we will try to help you. I know some of you had some questions yesterday about registration. I hope that you managed to register in the end, but please let us know if you still have any challenges. All right, so for those of you who are already logged in, as you can see here, I'm in the workspace and you can click on either Desk Workshop Part 1, or you can also look at the material in the Shared A folder. I'm going to go into Desk Workshop Part 1. And today we'll be looking at ground-based observations, which are very useful for validating satellite observations, further improving models that are already in existence, and also developing new satellite algorithms for monitoring dust and sandstorms. So let's begin first with AeroNet. So AeroNet stands for the Aerosol Robotic Network, and it is a federation of ground-based remote sensing aerosol networks that are present across many countries. So if you like to take a look at all the Aerosol, all the AeroNet sites, you can click on this link here in the notebook, and it will take you to a map showing you where all the stations are, as well as the names of the various sites. You can see that there are parts of the world that are very densely covered, but then there are also parts of the world where we have some gaps in the network, as you can see in these parts where there aren't many stations located. So an important thing to note is that there are 3 different levels of data provided: level 1, level 1.5, and level 2. And these different levels of data have to do with whether or not they are unscreened, cloud screen, or level 2, cloud screen and quality assured. And there's also a time lag between when some of these data, higher quality data, are available. For example, level 2, there is a time lag of maybe up to 6 months or even longer, maybe up to 12 months, also because of the pandemic, as you will later see when we begin to download the data. So AeroNet provides a number of data types, including aerosol optical depth, which is what we will be looking at today. So to download AeroNet data, you can actually use a wget function, and it allows you to basically specify the start and end time for the data that you're interested in, whether or not it's aggregated on a daily basis, for example, the level of the quality, which station you're looking at or interested in. So let's take a look at how we can download some data. So the first step, we have to, as usual, load our libraries, and we'll be using these libraries today: NumPy, Matplotlib, Pandas, and wget. And basically, we want to end up with an example request that looks like this, which includes a URL that specifies the characteristics of the data we're interested in. So we'll be using wget to download the data from a web service, and we can use a dictionary here to set up some keywords that we want to use to describe the data we're interested in. So for example, we start off with the endpoint, which is this website here, and then the name of the AeroNet station. So in the example here, it's Palma de Mallorca. And then the year, the month, and the day of interest, which is the start period, the start time or start date, and then the end date, year, month, and day. And then the data type, whether you want, for example, AOD level 1.5 or AOD 1.0 or AOD level 2.0. So depending on whether you want, what level of quality you want, you can change this. So in this example here, it's level 1.5, but if you wanted 2.0, then you would just change this to 20. And then for the AVG parameter, this is basically asking you to specify if you want all points of the data or if you want the daily averages. So if you want the daily averages, you can change it to 20. So here's our data dictionary. And our next step is then to construct the wget request. And we use this using the format function. So basically, we are pulling the dictionary keys from our dictionary up here into this URL. And then it's already formatted for you. So when you press run on this cell, you will come up with the URL that we need to use. So now we're ready to download the data. You have to pass this URL that we constructed up here into the wget download function. And when we do that, we also need to include where we want to store this data, which will come to us as a text file. And so we have here specified the folder as well as the file name that we want to use to store the text. So now I have downloaded this data again, and now it's stored in my folder. So if I head back out here, I can actually see this file. It's already been downloaded once, which is why it was re-downloaded. So I'm in data, observations, AeroNet, and you see this is the file that I just downloaded. So since I already have one copy, I don't need this, so I'm going to delete it. Now we are going to do the same for the daily averages. So we have to change AVG to 20. And I can show you how to do this here again very quickly. So if you change this to 20, then I will again download, oops, I need to change the file name as well. So now I will have downloaded this again, and I can go back and refresh this to see the new text file that I've downloaded. Okay, so this was just a demonstration of how to download this data. And now let's move on. So once you've downloaded the data, you can read this into the notebook using pandas. And the next step is to use pd.readTable, and then you pass in the path of our data. And we recommend you to always open your data before you read it in, because sometimes you will get data which have a few extra rows of text, maybe describing the data set on the top, which you don't need, which is what happened here. And that is why we also then later specify the header, which is at the first row of text, which contains the information about what variables are in the columns. So as this is a comma delimited text file, we have to first set the delimiter to a comma. And then we set the header to number 7, because that is when we first see all these interesting header information that we need. And then we can also set the index column. And this allows us, by setting index column to the 1, allows us to set the date column as our index column. So as you can see now, we have a data frame that has 258 rows and 113 columns. And you'll also notice that there are missing data points, and these are all filled with minus 999.0. So we want to replace this with not a number. So you can use df or data frame.replace, and we say that, okay, we want to replace all the minus 999.0 values with numpy dot not a number. So once we do this, let me make sure that I'm also following along here. So once we do this, we will then see that the 999s are now replaced by not a number. So let's get an overview of all the column information available here. You can use df.columns.toList to get a list of all the column headers. As you can see, there are quite a number of different AOD values that we can take a look at different wavelengths. And there's also the angstrom exponent at different wavelengths. And the angstrom exponent is useful because it gives us a sense of how large the particles are. And for basically, if you remember angstrom exponent, the higher it is, the higher the angstrom exponent is, the finer the finer the particle size is. And dust tends to be a coarse particle size. So we will usually be looking for an angstrom exponent that is low to indicate that the majority of those particles in our AOD reading come from coarse particles or dust. So if you'd like to, again, narrow down the data set, in this case, we're only interested in the month of February, we will need to use the filter function. And let us take a look at the various angstrom exponent columns. You can also use that to select only certain columns that you're interested in. So in this case, we use df.filter, and we are looking for any column that contains angstrom. And we look at the first 100 or so values. And this gives us a data frame with 100 rows and 6 columns. And you can see that actually there's been a gap in the data. If we go and look a little closer at this time period, it's a bit clearer. So if you look at 40 to 80, you notice that there is a jump here from the 2nd of February to the 5th of February. So we have some gaps in this data between the 2nd and the 5th of February 2001. So next, let's visualize all the points from the data set. And we have several AOD information values that we have selected. And we can use the plot function of the pandas library to define this line plot. So let us take a look at the steps that are needed. We first have to initiate a matplotlib figure using plt.figure, and you can set the figure size here. And then we also define the axes. And next we have to define a line plot. So we first select the data frame columns that we're interested in. And we use this again using df.filter to select those columns. And we then instruct it to plot these data on the axis using a dotted line style. So the lines will have dots. Next, we will set the title of the plot here. We have specified a title, which includes the data type, the month, as well as the location of the station, the font size, how much space we want around the title. We can also set the X and Y labels here. So aerosol optical depth, and the X label is day. And then finally, we set the ticks to tell them how large we want the font size of the ticks to be. These are an example here. And then we also add a legend and a grid. So here's our legend here. And then we also have the background grid. So here's our completed figure. We have an aerosol optical depth values on the y-axis and then day on the x-axis. So you can see the changes in these values over time. And we noticed that there's a peak here between the 5th and the 7th of February. And then there's another large rise in values towards the end of February. So let's find out if these are actually dust and sandstorm events. Let's take a look at the angstrom exponent to confirm our suspicions here. So next, we are going to load our daily values, and we will load them together with the angstrom exponent. So this was the other text file that we created earlier on. So once again, we read in this data table. We give the same instructions about where our header row should be and which should be our index column. And now you see that this data frame only has 15 rows. So, and if you look, these are basically daily values. And again, we set our missing data value to not a number using the replace function. So let me make sure I'm following along here. And then we do the same thing that we did earlier on, except now, in addition to the AOD values at different wavelengths, we also add another line, which is the angstrom exponent. And we want to plot this as a bar with the color of light gray. So apart from that, all the other things are more or less the same. So now we have, again, the daily values of the AOD at different wavelengths, but we also have the bar that shows the angstrom exponent between 440 and 870 nanometers. And you can see that on these 2 days, the 5th and the 6th, where we have a rise in the AOD values, you see that the angstrom exponent is very small. So this is an indication that the particles are coarse and it's likely to be a dust event. And the same for the end of February here between the 20th and 21st. Looks like the angstrom exponent is also very small, but there's a large increase in the AOD. So this is again a potential dust event. So we have another station, which is Ispra in northern Italy. So let's take a look and see if we see a similar value in northern Italy. So we have again downloaded this data beforehand for ISPRA, and all this is the same. We have we're reading in the text file, the CSV. We replace the -999 values with not a number, and then we take a look at the data frame. And these are again daily values. And so if we plot this again the same way, we will notice that later on, it does appear that there is a peak here at the end of February as visible in ISPRA. And as you notice, the angstrom exponent also goes down, and this indicates coarser particles. So it's likely that there's some dust activity towards the end of February as well. Okay, so this is the first data set that we have covered for AeroNet. And next we will move on to a different data set. So once again, let's go back to the file browser here. And let's take a look at EarlyNet, which is using LiDAR data. And EarlyNet stands for the European Aerosol Research LiDAR Network. And this is a form of active remote sensing where there is a laser beam that is transmitted into the atmosphere, and then the backscatter is recorded by a sensor, and this gives information about even the 3D profile or how high this aerosol cloud is. So that is very useful information, as, for example, the higher the aerosol layer is, there could be a stronger signal for affecting other satellite-based indices. So this is very useful for comparing and getting a ground truth. Okay, so the type of data that's available are long-term multi-wavelength backscatter, as well as the extinction coefficient profiles. And if you want to take a look at the EarlyNet stations, if you click on this link, it will take you to a map showing you where the stations are located. And you can also see the station code, the country, coordinates, and information about which institutes are responsible for managing them. And the data format you will download the data in is, again, NetCDF. And once again, there are different levels of quality control. So there's level 1, which is basic, level 2, advanced, and level 3 are climatological aggregated products. If you want to download this data, you have to first register for an account, and then you can access the data from the EarlyNet database. So we were taking a look at ISPRA earlier on, and this is the same station that we will be looking at for the EarlyNet data. So let's begin by loading the libraries. And we have already downloaded the data in the data folder for you. So these are hourly files, and you can use the Xarray open_mf dataset to open the multiple files at once. So now we're loading the data for ISPRA, Italy on the 23rd of February. So let's go ahead and load that data. And you will see that the output is an Xarray dataset, and there are 4 dimensions: altitude, time, NV, and wavelength, as well as 27 data variables. And the data variable of interest is backscatter. So this is the one that we'll be working with in our notebook. And we can keep moving. So the LiDAR sensors give us vertical profiles of the atmosphere, and we can take a look at the altitude variable to see the resolution and extent. And when we take a look at what is available, we find that there are data levels or heights for every 40 meters. And it starts at 539 meters and goes all the way up to 8,159 meters, or around 8 kilometers. And as you can see, the units here is in meters. So before we visualize this profile, let's load the variable backscatter from the data set. And you can load this by, again, using the square brackets and then adding in the name of the variable as a string. So let us load the backscatter data into a variable called backscatter. And you will see that there are also additional attributes down here, such as the long name, in this case, the aerosol backscatter coefficient, and the units, which is in meters and per meter and steradian, as I've learned. So now that we have the data loaded, let's visualize this backscatter and see what the profile looks like on the 23rd of February. So once again, we are using matplotlib here to visualize this. So again, you initiate the plot, define the figure size, and define the axes. We have to transpose the information in order to plot it. And we also multiply it by 10 to the power of 6 for better visualization. We also state that our maximum and minimum values are between 0 and 2. And we also add a color map called Jet. This is something that you can also customize. And you can change the colors as you prefer in the future. Then we add the title and the axes here, as we have done before in the past. And this time for the Y label, we're going to use the units that are from the altitude attribute, and this is in meters. And then the X label, as this is hourly data, we'll use hour. Then we again set the ticks and define the color bar here and say that we want a vertical color bar. So you can see it plots like this. And you can set a label for the color bar as well, and tick parameters as well as a grid. So once you have all these described, you can then again run the data. You can run this, and it will generate this plot. So as you can see, these are the hours. So 11 o'clock, 12 o'clock, 1300 hours, 1400 hours, and you see that there is already some signal here beginning to appear. So let's take a look at the next 2 days, the 24th and the 25th of February. So these have also been loaded, pre-downloaded for you. And again, we do the same thing here with the open MF dataset, open the data files as Xarray datasets for the 24th and 25th of February. Then we can plot these 2 days in a slightly different way. We are going to plot this as 2 figures in one row. So we have a single row with 2 columns, and there are basically 2 subplots, one for each day. And here we are basically saying this is for the first subplot, and then this is for the second subplot. So we do the same thing as we did for the 23rd. And what we end up with is a figure with 2 subplots. And here you can see that the aerosol layer is beginning to come in at around 2 to 3 kilometers above the ground. And over time, it's settling downwards. And then on the 25th, you see that it has arrived at the surface level. And this strong aerosol event can also be seen in the EEA air quality data, where the PM10 value exceeded the World Health Organization's limit of 50 micrograms per square meter. So let's take a look at our next data set, which is the EEA data. And the EEA, or the European Environment Agency, they have a network of air quality stations all across Europe. If you want to take a look at these stations, you can click on the link here, and it will load a map eventually that shows you where the stations are, and you can also look up the station name. Okay, I'm not sure why this isn't loading. Let me try again, but I think we can move on for now. We'll check the link later on. And there are 2 air quality particulate matter limits that will be of interest to you. Basically, for PM10, for PM10, the mean value may not exceed 50 micrograms per cubic meter more than 35 times a year, and the annual mean value may not exceed 40 micrograms per cubic meter. As for PM2.5, there is no limit set by the EU, but the WHO limit is 25 micrograms per cubic meter. So you can learn more about these limits over here. And you can download this data again in the CSV format, and this will be in the form of daily aggregate data. So we have a EA air quality portal that allows you to download this data, and you can specify similar values to the AeroNet, from which year to which year, the country name, the city name, and there are a number of pollutants that are covered here. However, we are going to use a Python library called Airbase, which allows you to download the data for a single country at the same time. And you can specify what pollutants, similar to what I showed you earlier with the drop-down menu, so certain parameters of the data that you're interested in. So we'll start by importing the libraries, so NumPy, Matplotlib, Pandas, and Airbase. And we have already downloaded the data for you. It takes quite a while, but if you wanted to see the steps that we used, feel free to take a look at these code cells over here. So we use the Airbase library and load in the Airbase client method. And then we are interested in ISPRA, which is in Italy. So we download all the data for Italy, IT, and our pollution we selected was PM10. And we only want the data from 2021, so the start and end year is the same. And then you can use the function called download to file in order to download it. So first you specify a client request like we did up here, and then you use download to file, and you give a path to where you want the CSV to be stored. So to make it easier, we have downloaded everything into a single CSV. You can also download it into multiple files, but then you end up with hundreds of files. So we download it all into one document, into one file. Okay, so now that we've downloaded the data, let's take a look at how we can read it in. Once again, we are going to be using Pandas to read in this data. Unfortunately, for our data from the EEA stations, we don't have a station in ISPRA that we could use, but the closest that we found good data for is called Varese, and it's relatively close, it's a few kilometers away. And so we'll be using data from this station, which has the code IT1588A, and we'll be looking at PM10. So let's load in the file name, which has IT_PM10 from 2021. And we'll once again be using the same read table function. So when you open the file and take a look at it, you'll find that actually the data already is on the first row, so no problem for the header. So we just go ahead and put 0 for the first row for our header. And because we wanted the index column to be the air quality station, we looked for that and we set it to the 5th column, or position 4. And this is what you get for the index column. To avoid mixed type interference, we have set low memory to false. And when you run this will then read in the CSV into a data frame, which has nearly 500,000 rows. So we are only interested in one station with this code for Varese. So when you filter it, so that we use like, and we filter it to the station code, you find that we now have only 297 rows. And even though we have already found all the rows with our data of interest, there is still quite a few columns. And we are most particularly interested in the concentration column for PM10, as well as the date time begin column. And we want to reorder it so that date time begin is now our index column here, instead of this air quality station code. So we do that first by selecting the columns that we're interested in using the filter function. And then we reorder it so that date time begin is our first column, and then followed by concentration. Sorry, I misspoke. The index column is still at this stage in time, the air quality station code, and we are just reordering these two columns here. Okay, so we actually really do want date time begin as the index column, and that is what we will do in the next part. So we have to change the date time begin column to the index column by using set_index, and then we will resample this hourly data. As you can see, we have 297 rows here into daily data using and calculating the mean for each day. So first we set the new index column to be the date time begin. So this is what we get. And we convert this index to a date time index, because at first it's stored as a string and we need to make sure that it has a date time information. Then we use resample by day using the mean to get the daily mean. And then we rename this column to PM10, because before it was called concentration, and now we want it to be called PM10. And this is what we do. And this is the resulting table. So let's do the same for PM2.5 data. And we repeat all the steps that we did for PM10, and we end up with the same result, but with the PM2.5 data. And because we are only interested in plotting data for February, we need to filter the frames further so that it is only showing us data from the 1st of February to the 28th of February. And we can use this, we can do this using the index to series method. So first we pass this in here. So PM10 daily index to series between the start date and the end date, first and last day of February. And then we save this as a new variable called PM10 Feb 2021. And this is what we end up with. So we now have only data from the 1st of February to the 28th of February for the PM10 concentrations. And we do the same for, let me make sure I also run this. And then we do the same for PM2.5. And then finally, we will plot this data for Veracer in a matplotlib figure. So once again, we define the plot. We add the two data frames that we want to plot. So PM10 as well as PM2.5, and we give them each a label, and these are going to be line plots. And then we add an extra line to show the PM10 daily limit, which is at 50 micrograms per cubic meter. We set a title for the entire figure, which is shown here. And then the X label and the Y label. So the Y label is here on this side, and then the X label is day, which is here. Then again, we set the ticks. We want this time to have a darker line, a major tick every 10, every value of 10. And the same we do again. We can also change the size of the grid settings, how thick the lines are. Then we add the legend, and then we show it. So when you run this code cell, you will produce this plot here. And as you can see, at this 50 micrograms per cubic meter limit, it was exceeded a few times in February. So the first time, I guess, in the beginning of the month, and then again at the end of the month for PM10, which is the blue line. So this is an overview of the ground-based data that you can use in addition to the satellite data we covered yesterday. And now I will hand this time over to Julia to share with you about the model-based data you can use.
Okay, thank you, Sabrina. Because we are already, again, more than an hour into the session, almost like 1.5 hours, I propose maybe before we now go to the model-based data that everyone takes a 5-minute break to get something to drink, to get up, to move a bit. And then it is now, so let's resume the session at 25 past, so around in 7 minutes. And if you have specifically questions to ground-based and in situ observations Sabrina introduced you, feel free to go on Slido or also post them in the chat. And before we then go over the model-based data, we can also address your questions. So see you all 25 past. Data discovery session. I just also share my screen. And this is a familiar interface by now for everyone. So we already had now an overview of satellite-based data, which we showed you and gave an introduction to on Tuesday. And now Sabrina introduced you to 3 different data sets related to ground-based observations. And now, and you probably also saw that all the different data sets we covered, they all highlighted a specific dust event that happened at the beginning of February last year in 2021. And now we would like to go to the model-based data. We will introduce you to 3 different model-based forecast products. And this gives us now a good opportunity also to verify or to see how these model-based data actually forecasted the specific dust event that occurred over Europe at the beginning of February 2021. So if you go to this training platform, you see a folder with the number 3 model-based data, and this is where we are heading to now. And the first model data or forecast data we would like to introduce you to is the regional model or dust forecast data of which is part of the WMO SDS WAS initiative, and which also Sarah already introduced you to. And so this notebook, if you open the notebook, will introduce you to the variable dust optical depth, and you will learn how the dust event that occurred at the beginning of February 2021 was covered or was predicted by this forecast data. The notebook gives you additional background information about the WMO sand and dust storm warning advisory and assessment system, and so what their objectives are and additional information. The forecast data that is provided under this framework provides forecast information up to 72 hours in advance on a 3-hourly time step. And there are 2 different variables or parameters available: dust optical depth and dust surface concentration. But this notebook only covers the dust optical depth. The data is available in NetCDF, and we also linked you a link where you can download the data on the website. You see that you basically are prompted or asked to log in order to download the data for this specific training course. And if you open the notebook, you will see here general access credentials, which you can use specifically for course participants to download the data. So there has been a generic user created with a Gmail address, and the password you also see or you find in the notebook. So if we Let's just go there and log in with these credentials, that you also see how the data access system looks like. Okay, and so basically you see here the website where you can download the data. If we go more to an overview of the forecast products and dust forecasts, you let's go here again. Then you see an overview of different products that are available. And if you go then to files download, you will get a list of different model data that is available. So from the Barcelona Supercomputing Center, from Copernicus, and other modeling organizations as well. The specific data we are interested in is the data from the NMMB Monarch model. And if you get, and on the website, you also get more, you can get to, or you can get a reference to additional information about the model itself. And if you go to public data files, you are then get a list of different years, and depending on the year you're interested in of the forecast, but it is also regularly updated. So if we go, for example, to this year, to 2022, then we see for January the data, and then for each of the days you get the forecast up to 3 days in advance. And the last forecast here has been issued yesterday on the 25th of January, and it will be updated again today with the 26th of January. And this is also how you can download it. So if you then click on a file here, then you see that the download automatically starts and the file is downloaded. And this is also what we did already for you for the dust event in beginning of February 2022. If we go, just that I can also show you, if you go again to the main folder and then to data, to the third folder model, and then the data from the SDS WAS, then you see here a forecast from the 5th of February 2021. And this is, so we downloaded one forecast file from the 5th of February 2021. And this is the file we will be using in the notebook. So I just also go back again to the main data folder in order to be able to access the other notebooks as well. Okay, good. So feel free to have a look and try out to access the data. If you have any issues, then please also write it on Slido. This is something very important also for you because next week, in case you signed up for the practical workshop, we will ask you to also physically or to really download data. So we will not have the data prepared for you. So this is important that you also have access to the data download here. Okay, then we start as we start always in Python. We load a range of different Python packages and libraries. For these examples, and also the nice thing with model data is that we actually can use the X-array library, because model data, because it is modeled data, it is very standardized and very regular. And this is also what we do. So we basically only need matplotlib to visualize the data and X-array to prepare and load the data, because the data is disseminated in netcdf. So we again also make use of the functions that we introduced you to, and we load all the functions that we can also use them in this notebook. And so the first part is then to load the dust forecast data, and to better understand also how the data is structured, and also what information the data provides us. And we first define here the path to the file, which I also just showed you. So we have one file from the 5th of February 2021. We define the file path, and then we apply the function open_dataset from the X-array library to open this netcdf. Because we only have one netcdf file, it's very simple. We can just use the function open_dataset. And if we do this, then we get a X-array data set is loaded. And the X-array data set, this is important to differentiate between an X-array data set and the X-array data array. So a data set is a collection of different variables that all share the same coordinate information. And so what you see here is that we have 3 dimensions. So we have latitude and longitude, and we also have 25 time steps because we have the forecast up to 3 days ahead every 3 hours. And we also have 2 data variables. So we have the dust surface concentration and also the dust optical depth. And both data variables show or share the same coordinate information for time, latitude, and longitude. But a data set itself doesn't give you access yet to the data itself. So if we want to really work with the data, we want to manipulate maybe the values, or we also only just want to visualize the data, we have to first load the specific data variable and the associated data array to this data variable. And I will show you in a bit how to load this data array. But then the data set additionally gives you also additional metadata when the data has been created, under which convention, etc. So some additional metadata that can be useful. So as a next step, first, let us understand a bit better the dimensions of the data set before we load also the variable of interest. So we have 3 dimensions: latitude, longitude, and time. So if we if we have a closer look to latitude and longitude, we can load these dimension information by specifying the dimension name from our data set. So we call it, we can just use a period and then the name of the dimension. And with this, we can load the information as a data array. And here we see that basically the data has a resolution of 0.1 times 0.1 degrees and is not a global forecast. So if we have a look to latitude, we see that we have latitudinal bounds between -11 degrees going up to 71.4. And for the longitude range, we have a range from -63 degrees to around 101.9. So this is also important to understand, okay, it is a regional dust forecast model, not a global model. And then the next step is to also to see a bit more, to better understand the time steps or time information we have. And if we load the information in the same way as we did for the latitude and longitude coordinates, we see that each model or each forecast, so the model run is each day at 12 UTC. So for our data, we have the forecast data from the 5th of February. We have the initial run at 12 UTC. And then for every other 3 hours up to 3 days ahead, up to the 8th of February at 12 UTC, we have a forecast information. And so the next step is then to load the data variable as a data array, what I explained before. So from our data set, we load the actual data values, and with these data values, we can then further analyze, process, and visualize the data. And so we load, so just as we load the variable optical depth here. So we can do it in the same way as we did for the coordinate information or the dimension information. We specify our data set and then period and then the name of the variable of interest. And if we load the data array out of our data set, because what we expect is to have still the same dimension. So we still have 25 time steps and latitude and longitude information. But additionally, we now, instead of getting additional metadata on a file level, the data array provides us additional metadata on a variable level. And this is often much more useful also, that can be used later for visualization, because now we see that this variable is the aerosol optical depth. And additionally, we also see that this variable is unitless. But if we had a variable that has a specific unit, it would be also defined here. And this is also always very helpful. So because we want to make use of these attributes that are part of our data array, we just also define additional variables. We call them long name and units, because these variables can then be used for visualization, for visualizing the aerosol optical depth at 550 nanometers. So now this is the nice thing with model data. There is not a lot of data preparation in beforehand, because it is a very regular, well-structured data set. The only thing to do is loading the data variable. And now we're actually already in a position where we can visualize the dust aerosol optical depth from the regional monarch model. And we can do this again with the function visualize p color mesh. Sabrina introduced you to this function already on Tuesday. And this function makes combines two very powerful plotting libraries, matplotlib from Python and also CartoPy. And CartoPy gives us very powerful projection options to visualize the data in different projections if it is needed. So this function is quite flexible, and you saw many examples that you can use for satellite-based data, but we can also use model-based data to visualize. And so what we do here is that we first now only visualize one time step. So we selected here a time like the 6th time step. So the 6th step forecast step, starting from the 5th of February at 12 UTC. And we specify here the data array with the forecast step, because our data array still has 3 dimensions. So we have to specify which time information we are interested in. Otherwise, it would give you an error, because the plotting library doesn't know which specific time step you're actually interested in, because it is a 3-dimensional data object. Then we specify the longitude and latitude information, the projection, which we want to have a regular plate carré projection. We also define the color scale. Here we use like the hot color scale option, but this is also one thing we really invite you also to play around with. So maybe there is another color scale you find more appropriate to showcase for dust data, then this is also something we can also discuss next week, but this is something you could really play around with. Then we make use of our variables, of our metadata that is given by the data file and by the data array. And so we specify the unit and also the long name. And additionally here, we also add the timestamp information, because this helps us then also to understand for which time or hour the forecast step is in fact valid. And then we specify the minimum and maximum value of the aerosol optical depth. And then these keywords are optional, but because it is a regional model, we set the keyword argument set global to false, and the data we are interested, or the bounding box information we take from the minimum and maximum bounds from the data itself. If we would, or if you set this keyword argument not to false, but to true, then basically you would see the entire globe. But in the end, because we only have data for this geographical bounding box, it would not be very specific or not easy to actually detect. That's why we set it here to the actual bounding box information of the data. And if we do this, then you see basically the bounding box for which the data is valid. So it covers Europe and also Northern Africa, and specifically also the Saharan region. And we see it already that this is like the 6th forecast step. So it is valid for the 6th of February at 6 UTC in the morning. And you see basically that there is already dust forecasted coming to Europe and already affecting southern Germany and also here the Mediterranean Sea. And as a next step, because it is forecast data, it would be also interested to actually animate the forecast up to the 3 days ahead to better understand how the aerosol optical depth might evolve over the forecast period. And this is what we do in the next step. So Sabrina also already introduced you to this code, to the animation code that can be used in order to animate geographical data via Python. So the animation function can be divided in 4 different parts. So first we set the initial state, which where we also again use the visualize p color mesh function, and basically we copy paste the visualization code we have here. With the only difference that we say our initial state is the initial forecast run at on 5th of February at 12 UTC. And this is what we do here. We then specify the number of time steps or the number of forecast steps over which we want to have the animation going over. And then we have also a function that is called draw, which allows us to, for each of the time step, we say, please update this, please update our initial state with this function. And there we say, okay, for each step, we want to update our time step. And so instead of 0, we specify here a running parameter, which we call I, to update for each of the time steps. And the same we also do for the title. And then we can use the func animation function from the animation package in Python to define our animation object. And then in Jupyter, we can make use of HTML library as well in order to integrate directly videos into Jupyter. And this is what we do here. So if you let run the notebook, it might take a while, especially to have this these 25 time steps or 24 time steps loaded from the data. So if you wait a bit, it will execute, and then you see basically here the development of the aerosol optical depth from the Monarch model over a period of 3 forecast days starting on the 5th of February at 12 UTC. And if we again wait again until start. So you really see that, yeah, at the beginning of the 6th of February, it really goes over it, or this event was predicted to influence France, Germany, and also the Mediterranean Sea here in this region. Okay, so I'd then go over to another model data. So we had a regional dust forecast model now from the Barcelona Supercomputing Center. And the next step would now to introduce you to a global atmospheric model that also offers you information on dust aerosol optical depth. And this is the second notebook which I opened here. And this gives you an introduction to the global atmospheric composition forecasts from the Copernicus Atmosphere Monitoring Service. And specifically, it highlights the variable dust aerosol optical depth. We also provide you again additional information on the CAMS Atmosphere Monitoring Service and also the global forecasts that are provided under this operational service. Again here, this notebook covers the Saharan dust event that occurred over Europe at the beginning of February 2022. We see here, as when we see the basic facts, that because we have a global model compared to the regional SDS model, we see it's much coarser resoluted. So the Monarch model has a resolution of 0.1 degrees times 0.1 degrees. And now, because it is a global model, it has a resolution of 0.4, so around 40 kilometers. But compared to the Monarch model, we have now a global coverage. So it's not only focused on Europe and the Northern African part in the Sahara, but you could also monitor the dust events in other parts of the world. And it has a finer finer temporal resolution, because compared to the Monarch model, which gives you every 3 hours a forecast, the CAMS model has hourly outputs up to a lead time hour of 120 hours in advance. And the data is available since 2015 up to present. And the data is also available in 2 different data formats. So you can get it either as GRIP format, which is a very common format used in meteorology, or as a zipped NetCDF file. And we make use of this zipped NetCDF file, and we will also show you how you can unzip the data. So the data is available via the Copernicus Atmosphere Data Store, and we also linked you how you can access this data store. In case it doesn't work for you to directly open it with the link, because we had sometimes I have issues. For example, here, if you open this link, as a tip, I can just say you that you can open this markdown cell, and then you can just copy paste here the link to the Atmosphere Data Store. And if we do this, then you see here the access page to the Atmosphere Data Store. And so this is basically your entry point to any data that is available and accessible via the Copernicus Atmosphere Monitoring Service. You have a search interface where you can search for some data, or you can also go to data sets, which provides you an interface where you get a full list of the data that is available. Or also here on the left, you can also have a selection interface that might be helpful for you also to find specific data sets, specifically if you're not very familiar with what the Atmosphere Monitoring Service offers. So the data we are interested in is we go to product type and then we go to forecast data. And there you see that there are two forecast types. One is the global atmospheric composition forecast, which we are introducing just now. And another one is also a regional model. It is the European air quality forecasts. And I will introduce you to this data set just after this notebook. So if you go to the CAMS global atmospheric composition forecasts, you get here as well an overview of what the forecast data offers you. It offers, again, like the horizontal coverage, the resolution, also the temporal resolution, and an overview of all the variables that are available from this global atmospheric model. And this is quite a few, so you see this list. So it is quite extensive. So it's not only related to dust, but really offers a wide variety of atmospheric parameters. So, but in order to download data, you have to go to the tab Download Data. And you have then two ways to download data. So you can either use it or you can do it via this interface in a, I would say, more in a manual manner, because you click here the data you're interested in, and you have a very, very easy to go through interface that allows you to select the variables and to specify the data of your needs. So we are interested in the dust aerosol optical depth is here. And then you see already if we specify it on the surface, so like only on one level, then a lot of additional fields that might be that you might need to specify are already grayed out, because we are interested on the surface on one level, so we don't have to specify the pressure level or also the model level. Then you can here specify the date. So I think I leave it, or I specify here just to show you. You can go back to different months. If you want to go back to different years, then you click on the months on top, and you can go here back to different years. We are interested in 2021, let's say also the 5th of February. And because it is forecast data, we also here only have to specify also the end date of the forecast is the 5th of February, if we only interested in the forecast of this specific day. Because you have to remember, with forecast data, we always have an initial run, and this would now give us the data of the model run on the 5th of February 2021 up to 120 hours ahead. So we will get the forecast of up to 120 hours ahead. If you specify here the 6th of February, you would get two different forecast runs. Or even up to 4, because the CAMS model provides you two forecast runs per day. So this is important also with model data to understand. So let's specify here as well also February the 5th. And we would, in order to harmonize it with the Monarch model, we can, for example, say that we also interested in the forecast run at 12 UTC, because if you remember, the Monarch outputs, or the Monarch model, is initiated every day at 12 UTC. And then, so we select the initial run of the model at 12 UTC, and then you can here select the list of the forecast hours you're interested in up to 120 hours ahead. And then the type is forecast. And you could either use the full model area, or also you can restrict it to a specific area you're interested in. And then at the end, they ask you to specify either grep or SIP-net CDF. If you go to SIP-net CDF, then you can either, or did I? Oh yeah, so we have to specify here the different, let's say we specify some lead time hours. And then here you see that basically in order to download the data, you have to be logged in and registered to submit a request. And this is also, if you don't have an access yet, then you can, we also linked you to register, or you can also go here and then you're asked to enter your email address and password or to create a new account, and then you can create a new account. So I can quickly also sign in with my email address and password. And oh, probably it's, if I don't remember my password, okay. So, and then basically once you're logged in, you can, then this green button is changed, or this button is changed to green, and then I can submit a form, and then you get redirected to an overview of all the data downloads or requests you have. And then you also see here that, okay, my data request has been executed, it is currently in progress, and once it has been executed and finalized, then I can also download it. So this is one way, and this is a manual option to download data manually on your machine. But then if we go back to this interface and to the form, you see here also again another option to show API request. And this is an option to download data in a programmatic way from the Atmosphere data store. And with this, you have to make use of a Python library called CDS API. And we will also show you how to actually retrieve the data. But basically with this API request, you can then also programmatically download data directly on the platform where you are working on. So if you work locally, then the data will be downloaded in a specific folder you can specify here onto your local machine, or here on the platform, you can then also download it directly to a folder on the platform. And this can be quite helpful, specifically also for next week, where we really ask you to also download the data by yourself. I will quickly also show you, so this notebook also has as an optional step an example how to retrieve the data in a programmatic way. So how you can use this API request to download data, but this is optional because sometimes it can take a bit to download the data depending on how many people currently access the data or ask for data from the Atmosphere data store. And for this specific example, we also made you already available the data. But for next week, it's also good for you to see how you can actually request data. And so let's start with the notebook. Again, you can load the Python libraries and the functions. Because the data is again available in NetCDF, the two main functions we need is actually xarray, and then or the three main libraries we need is xarray, matplotlib, and cartopy. And so basically how you can register, or how you can access data with the CDS API is first that you have to register via the ADS registration page. And again, if the link doesn't work for you, then just activate the cell and copy paste the links in a browser window. And once you registered, you have to be logged in. And then you can go to an API how-to page. And if you go to this page, I then basically it will show you here a URL and key. I will go back again, but a URL and API key, which you can then copy paste into this folder or into this code cell here in order to access the data. And this is important here. So you have to replace these hashes with your personal key, which is shown in the terminal window once you are logged in. And then you can load the CDS API library. You can specify or you can initiate a CDS client based on the URL and your specific or your individual key. And if you registered and you can copy paste this API request, you can specify also here the folder where you want to have the data, and then you can request the data in a programmatic way. Because the data is downloaded as a netcdf zip, we need an additional step to also unzip the data in order to actually have access to the real netcdf files. And this is an example how you can unzip data with the zip file library in Python. So basically, we just specify where our zip file is, the folder path, and then we say, please, from this zip file, extract all the files that are archived in this zip archive. And then we can again, so let's just have a look what data is actually extracted from this zip file which we downloaded. So if we go again to our main data folder, to the data folder, and then to model, and then to comms, then to the global forecast, we see here a netcdf file. Here we downloaded the forecast from the 4th of February 2021. And if once we unzipped the data, then we have in principle a data file that is called data.netcdf. So we have one data file. And if we load this with the function open_dataset, then we see here again, we have one data variable because this is the data variable we chose in our data request. And we also have again 3 dimensions: longitude, latitude, and time. And so the next step is then also to inspect more the dimensions in detail. So we start here with the time dimension. We see that we have 31 time steps. So we made it coherent with the model outputs from the Monarch model, or with the forecast from the Monarch model. So we also chose the runtime at 12 UTC and every 3 hours up to, I think, 96 hours ahead. So not a full forecast steps available. We chose, so only a subset. And then the latitude and longitude show us that we have now a coarser spatial resolution of around 40 kilometers, so 0.4 times 0.4 degrees. And then you also see in the longitude information that this happens quite often with model outputs, that the longitude is in fact on a grid going from 0 to 360 degrees. And in order to bring these onto a grid that we can also visualize it from -180 to 180, we need so we have to reassign the longitude coordinates to a grid that is going from -180 to 179.6. And this is what we do here. And once we did it, then you also see that the longitude values are now reassigned to a grid that we are more familiar with. And then the next step is to, from our loaded data set, to also load again the data array, which has the actual values of dust aerosol optical depth. And again, it gives us additional attributes. So we see here that it is dust aerosol optical depth at 550 nanometers. And again, it is in fact unitless. Again, what we had also for the regional forecast outputs, we specify or we make use of these attributes because they are quite useful for us when we want to visualize the data. So we specify a variable for the long name and also for units. And we also do the same for the coordinate information, latitude and longitude. And then the next step is again also to visualize the data. We make use again of visualize_p color mesh, and which combines the two functions or the two libraries, matplotlib and also the CartoPy library. We see here again, so we make use of, so we specify the data array. Here, important again, we have to extract one time step because otherwise the function does not know which time step or how to deal with these three-dimensional data. Then we can make use of the variables we just defined for longitude and latitude. We again set a projection to plate carré. We make use again of a color scale and also the units and the long name. And the minimum and maximum value, again, we set it to the same as we had for the regional forecast outputs. And you see the difference here is because it is global data that we don't set the keyword argument set global to false, and this function also works if we don't set these keyword arguments at all. And if you execute this cell, then you see basically for one time step, because we started on the 4th of February for these forecast data here, we have now the 10th forecast step is valid for the 5th of February at 6 p.m. UTC, so at 6 at night. And you see here the dust aerosol optical depth for this time step. And then we can now, because you see the global level, it's not so easy to actually identify for our region of interest. So the next step is that we can now create a geographical subset for Europe. This helps us just to specify more our region of interest for the specific dust event, because it specifically impacted Europe during this time. And so we also have in the functions library for this example a function which is called generate_geographical_subset. And this allows you to, based on latitude and longitude, minimum and maximum bounds, to create to clip a data array, or to subset a data array. And so you what you need is the data array you want to do a geographical subset of, and then you have to specify the 4 geographical bounds. And here we specify the 4 geographical bounds, and then we just apply them here to the function. And if we now compare, so once it has been geographically subsetted, if we compare now our latitude and longitude information, before we had 451 entries for latitude and 900 entries on longitude. And now we really only have a subset for 107 entries on the latitude and 162 entries on the longitude. And if we again visualize the subsetted data array, but this time because we want to have only the European focus, we use the keyword argument set global to false, and we can also specify the longitude and latitude bounds, which we also just specified before. And if we again visualize this, then we see here now our like a European subset and the dust aerosol optical depth on 6th of February 2021, starting to impacting southern France and also parts of northern Spain here. But you see here that like the causal resolution, you see much more detailed once we focus on a geographical subset. And then we can do the same again, what we did for the monarch forecast outputs, because this is the nice or the interesting part of forecast data to also better analyze and understand how the forecast will develop over a specific, over the forecast period. And then we again just animate the data. So this time, I think we have 31 time steps. So we specify 30 frames because Python starts at 0. So it's always one step less because we start at 0. So it's like the 31st step is actually frame 30 in the array. And if we then execute the animation again and we show it as a video in the notebook and we start the animation, then you also see here the global or the global forecast output from the CAMS global model on dust aerosol optical depth over this time period at the beginning of February 2021. And so the forecast also predicted dust intrusion over Spain, France, and also parts of Germany later on. Okay, so now we introduced you to two different models and also with different specifications. So the first one was a regional model, which provided specifically dust forecasts. Then we also introduced you to a global forecast model, which also offers a variable on dust aerosol optical depth, but also offers you many more atmospheric parameters. And now we want to also introduce you to, let's go back here to, this is data. So I just go back here to the main folder to another data product or the forecast data set that is available as part of the Copernicus Atmosphere Monitoring Service. And this is the European air quality forecasts that is offered by CAMS. And so we are now, from the global forecast, we are now going back again to a regional model output, and which has the advantage again to have a much better resolution, but it only covers Europe, so it doesn't allow us to also have a look to other parts of the world, the dust forecasts. But we have the same temporal resolution that offers us the global model. And here, this is also the important thing to notice is that these European air quality forecast data from CAMS are provided on a 3-year rolling archive. So if we go to our Atmosphere data store and we go to data sets, and we look again to forecasts, and we see here the CAMS European air quality forecasts. Let's go there. Then we see here all the information that we also provided you. You also see that the data variables that are available as part of this regional forecast outputs are much less than the variables we can make use of the global forecast model. But we also see we get here a sorry, am I now? So we have here a dust variable, which is helpful for us for our interest in dust monitoring and forecasting. And you also see here basically the variables that you can choose, and also different type of models. So you can get here more information about, so you can either select a specific model from different, and they're like 2, 5, 7, 9 models available, or you can also make use of the ensemble of the different available models. And the ensemble is basically taking all the model outputs and creating the average of multiple models. And but here, this is the important thing to notice, is that basically if it is on a 3-year rolling archive, so we are in 2022, so you will be able to access data until January 2000, or from January 2019 up to now January 2022. If you try to access data in 2018, you will get an error message. And this is important to understand, so that this data is only available up to the past 3 years. And then again, you can get this data either via manually via this clickable interface to manually download the data, or you can also click your data of interest, and then you can see the show API request. So this is the same mechanism. Important is that you have to double check that you are logged in. And then you can either download it to your manually or in a programmatic way. And this is again here what we also added as an optional step. So in order for you also to see what type of data we downloaded, and then also the specifications of the data, we included the data access in the notebook, but it is optional. So for this training discovery, or for this data discovery, the data is already downloaded. Just to also show you that these European air quality forecast data is available either in GRIP or NetCDF. So here it is available as NetCDF. This means we don't have this additional step that was needed for the global forecasts to unzip the data. And then basically, again here, if you're interested in retrieving the data, you see again that so we specify for 1 day the date, the forecast we're interested in, the variable, the type, the runtime, and then the lead time hours. And so here we specified every 3 hours as well, on a single level, so on the surface. And if we just go back to our data folder, and you go to 3_model, and then to CUMS, and then we go to European forecast data, you see that basically in this folder, you see that this is the data file we also indicated here. So it is the forecast on 4th of February 2021, and it shows the dust concentration. And it is a NetCDF. So as we are by now very familiar with NetCDF files and also the Python packages, or we know the Python packages that we can use to open NetCDF files, we again make use of the X-array dataset, the X-array library, and the function open_dataset, because we only have one NetCDF file, and so that's quite easy. If we execute this this code cell here, then our X-array dataset is loaded, and we see that we have now 4 different dimensions. So we have longitude, latitude. We have one dimension that is called level, which only has one entry on this dimension, and additionally, again, 31 time information or time steps or forecast steps. and one variable, what we chose, which is dust. And so first we can inspect again the dimensions. And here, when we start with time, we already see that this is not in a format that is very familiar with us, I would say. And so we know that the time steps consist again of 31 time steps, but we see that the time is in nanoseconds. And so, but for us, for visualization, for visualizing the data, or in general as well, to better understand for when the forecast is valid, we would like to convert the time information into a human readable format. So in the best way, what we had before, that we know for what day and also for what hour on the specific day the forecast is valid. And this is what we do in this next step. So we first, based on the long name information we have of our data set. So the only information we get from our data set is under attributes, and then the forecast. We get here that we know that this is the forecast on the 4th of February 2021. And so, or also on, under the long name, sorry. So here under the time dimension, and the time variable also gives us an attribute which is called long name, and here we get the timestamp for when the model run was initiated, or for what on the day the model run was initiated. And so we take here this string from this attribute long name, and we create a timestamp variable. And then we convert it into a timestamp, a datetime object. And then we see here that it is a datetime object starting on the 4th of February 2021 at 0 UTC. And then in the next step, we use the length of our time dimension, which is 31 steps. And we know that it's like a frequency of 3 hours, and we then build up our data object or data time index. So we used our initial time step, and then we say use the length of the time dimension with a frequency of every 3 hours, and we want to have this specific format for our daytime index object. And the result is then a more human readable timestamp information, which we can then also use to visualize the data later on. And so once we specified here this daytime index object, the next step is that we want to assign this daytime index object to our time coordinates. And this is what we do here. So we use the function assign_coords, and we say to our time dimension, please assign the coordinates new and use this daytime index for it. And if we do this, then we see then instead of our nanosecond, we have now our human readable time format. And then we can have again a look at the latitude and longitude information. And we see here now that we have now again a resolution of 0.1 times 0.1 degrees. And again, our longitude information, we have here longitude information that is around or higher than 300 degrees. So it is again on a grid from 0 to 360 degrees. And we reassign again also the longitude information so that it is brought onto a grid that is going from -180 to 180. And if we then double check our longitude information, we see that the coordinate information has been reassigned. So we have now a better understanding of our data. So we loaded our data set. We have now a better understanding of our dimensions. For this data, there were even some additional steps required to better work with the data, that we also know when our forecast is valid for. And now we can again also load from our data set the specific data array and our data variable, which is the dust surface concentration. And this is here we load the data variable. And again, once we loaded our data array, we get additional attributes. And we see here the species, the standard name, and also the units. And so different to the other variables which we showed you for the other model forecasts, this is really the difference here, that it is like dust concentration, which also has, which is not unitless, but it has a unit micrograms per square cubic meter. And so again, we want to make use of these attributes that the data gives us. And so we specify again here variables, long name and units, and also additional variables for latitude and longitude. And then we are again in a state, or we are in a state where we can visualize the dust concentration in Europe on a specific forecast step. We make use again of visualize P color mesh and the Cartopy library, so which combines matplotlib function, P color mesh, and the Cartopy library. And because again we have here a European focus, we have to set the keyword or we want to set the keyword argument set global to false. We want to make use of the bounding box information the data provider provides us, because it already has a regional bounding box. We use all the same settings as we had for the other forecast data, just because we have now the mass concentration of dust in the air. We also have a different maximum value, and we set this here to 300. And when we do this, then we have here now for one forecast step, it is the 21st forecast step on the 6th of, and this is valid for the 6th of February 2021 at 3 p.m. In the last step, we can then also animate these forecast data over the forecast period, which we downloaded data for. We again set our animation functions to that it starts with the first forecast step, and then it is updated every time with the specific frame. And if we do this, we can integrate also the resulting animation into the Jupyter Notebook. And if we then let the forecast animation develop, we basically see also how, but in a much more regional specific detail, how the dust event affected or had an impact over Spain, and primarily Spain and France over this period. So with this, we are already a bit over our time. So because you saw that many of you had questions specifically to model data, we introduced you now 3 different data sets, 3 different model forecast data with a global focus, but also with a regional focus, which you can use for dust forecasting and dust monitoring. And I just would like to see if we have some additional questions, but I think also Sabrina already responded to some of the questions on the chat. I don't want to take too much time now from you. So this was now the second part of the data discovery week, of the data discovery part of the first week, where, and this week had an aim to introduce you to different types of data related to dust monitoring and dust forecasting. And for those who then applied to be part of the workshop next week, we really again also recommend you to go through the notebooks we prepared and presented you this week again in your own time. So you have now time over the weekend, and because this will be the basis of the workshop next week. And next week it will be less talking from us and more doing from you. And this is important because now the examples we showed you, you have to now put into practice, and you really have to work trying to get data, because then you also just realize that it's maybe sometimes not that easy, or you are unsure which settings you have to set or which data you actually have to select. And this is next week a very good opportunity for you to work yourself with the data. With this, I thank you all again for your concentration today, and also for participating to the session. And then we look forward to see many of you next week again during the practical workshop. And I wish you a very nice remaining day, and thanks again for joining today.